Okay, so good morning. Could you solve the problem? Not yet. Yes. What do you have the answer or not?
It's 1/4, right?
1/4, I see it is involved in the solution, but I ask you for finding sine of c. Do you say that this is 1/4? If I have done my calculation back then right, the answer is not 1/4. But somehow 1/4 gets involved. So how should I solve the problem? Of course, my figure is really poor. We had the precise figure last day, but here, first of all, let me convince you again. This triangle here is an isosceles triangle again. Why is that? It's very, very poor here in this picture, but if this is going to be 90 degrees, so it means that this angle and that angle both are equal. And you are telling me that CD is the angle bisector, so this angle 1 and 2 are also the same. And then you see that this line, let me call it for example CG, this CG is also common for these two triangles. So based on angle, side angle, these two triangles are actually congruent. So it means that the triangle BGC is congruent to triangle MCG. Yes? And then I can conclude immediately that the corresponding elements, for example BC and CM here, are the same. Yes? But on the other hand, MC is also equal to AM. Yes, because of that assumption that BM is the median. So this means that AC is 2 times larger than BC. And of course, AC and AB are the same, so it means that AB is also 2 times BC. Of course, I have forgotten to write that this is an isosceles triangle, but that is the previous problem. Yes? So this is what we get. Is that understandable? Okay, and then what we do, we can write the sine rule for this angle and its side opposite to it, writing BC divided by sine A is equal to AC to sine B. Agree? Is that okay? Okay, and then I can use these properties. Yes. Instead of A, do you agree? So instead of B, I can write, because my point is to find angle sine of angle C, there is no difference between angle C and angle B because that's an isosceles, yes? So here, I would write it as, this one, I can write it as sine C, which is my unknown. BC, but I don't know why, so I don't think we need this one. Yes, we don't need this one. Instead of AC, I put 2BC. And instead of BC, I just put BC. The good point is that I can simplify it. But the problem is that still I have two unknowns. One of them is angle A, one of them is angle C. This is no problem because I can just get rid of it. So what should I do? I know that the sum of the angles should be 180, yes? But of course, I know that these two angles are the same, so I can write it as 2C plus A. And that's equal to 180. So this means A is 180 minus 2C. So I can write it as sine. Instead of A, I can write 180 minus 2C. And then you can see that if I divide both sides by this, and of course this is not 0, this is the length of this, what is left for me in the numerator is 1, But what is this? What can I write instead of this supplement angle? Sine of the supplement angle is equal to the sine of the angle. So it becomes sine of 2c is equal to 2 over sine c. Okay, then what? Can you tell me? So that at least this is good. I can write this, the product of these two is equal to the product of these two. So this becomes 2 sine 2c is equal to sine c. This is a trigonometric equation. I have only one unknown, and that is angle C. But of course, I don't need to be careful about all the angles, because here these are the angles of a triangle. I don't need to be very careful about that. So what should I do then? How should I find? But of course here, they haven't asked for finding exact value C. Probably it is not possible. They have just asked you to find the exact value of sine of C. So what should I do? Yes?
Use a double angle formula.
Double angle formula. And hopefully you remember. So what is the double? So sine of u of 2u is equal to 2 times sine u cosine u. Yes? This is the formula we had in Math 4. So then it means that I can, of course, I have an extra 2 here, which will be multiplied by that 2 from formula. It becomes 4 sine c cosine c is equal to sine c. Yes? Here I can safely divide by sine c, because sine c is definitely not equal to 0. Because if sine c is going to be 0, c should be 0 or 180, which is of course not possible in this context. So I am on the safe side if I divide by sine c, and then what is left for me is cosine c. So this is why I told you that 1 over 4 is involved, but that is not sine c, that is cosine c. But then you have the formula so that you can find sine c, yes? So you write sine squared c plus cosine squared c is supposed to be equal to 1. We already know that, so this becomes sine squared c plus 1 over 16 is 1. So this means that sine squared c is 15 over 16. And then sine c becomes plus or minus. But of course, in this context, which one is acceptable? Because c, the positive one. Because the c is the angle for a triangle. It can be between 0, I don't know. Of course, for this cannot be even bigger than 90, yes? So that is in the first quadrant, so it means that the positive sign is acceptable. That's one problem, for example. Yeah, that was a good example related to this. But I think it was more interesting if you want to draw this using GeoGebra. I think you also learned that one as well. Okay, any questions? Now let me give you a definition here that's also very common. Let u, v, and w be vectors. Okay. The product u dot v cross w is called the triple or sometimes mixed product of u, vector u, v, and w. Yes? First of all, I want you to tell me, is this combination, so you see there is no new operation for us here. So, but I'm just defining, this is very common in vector calculus. This combination appears a lot of places, so this is why we give it a particular name. It's called triple or mixed product of u, v, and w. Is it meaningful or meaningless? And what is the answer? Is the answer a number or a vector?
It's meaningful.
It's meaningful.
It's a number.
It's a number, yes? Because v and w are vectors. We learned that if we cross product them, the answer will be a vector. On the left hand side of this dot product, I also have vectors, so it is meaningful. And because that finally it's a dot product, it would be a number. Okay? We want to understand from geometrical point of view what that number is. Okay? What is this number representing for us? Okay. Of course, if I write this, I don't want to do this. Usually in some books you see they write it like this. Okay, without having pair of brackets around that. This is also not ambiguous that much. I always prefer to put the pair of brackets, but because you might say that there are two ways of interpreting this, you are right, but if you want to give the priority to the dot product, then it becomes meaningless. Yes, because if you do the dot product first, it becomes a number, and you cannot cross product a number with a vector. So even though it's a little bit ambiguous which one I have to do first, but if you think a little bit further, you will realize that this one is not possible to do first. So automatically I have to do this one first. So automatically a pair of brackets should be around the second pair. Yes, even though I don't like this, I avoid using this. But if you see it, there is only one way to interpret it, and that is this way. Yes. Now the point is that I want to understand what is the geometrical meaning. Can I give a geometrical meaning to this product, three vectors? So because there are three vectors involved, I will, if I have two vectors involved, then I can make a parallelogram out of them or something. And then do you remember that? What was the geometrical meaning of that? Yesterday we had the norm of this would be the area of that parallelogram, yes? Now here we have three vectors. If these vectors, all of them, lie on the same plane, what will happen for that? I mean that this will not be very interesting for us. Assume that I have three vectors like these pens, and all of them lie on the same plane as this desktop here. What would be that number for these three vectors that you see here? This red one, green one, and black one. Yes?
0.
It is 0. Why is that? Because, for example, let me say this red one is u, this green one is v, and this is w. So I have to multiply v by w. So what will happen? So it becomes a vector perpendicular to this plane. Yes? And it is the direction would be up if this is v, this is w. So then this vector is perpendicular to the plane. It's automatically perpendicular to this one as well. And the dot product between two perpendicular vectors becomes 0. So there is nothing very interesting if these three vectors are lying exactly on the same plane. So the interesting thing will happen that if I have two vectors in a plane, this is inevitable, two vectors, if they are not parallel, they will make a plane, and the third one will come out from it. Yes? And then we want to see then what is the meaning of that triple product. Is that understandable? So the interesting, what I'm saying is that if they are, by the way, if they are on the same plane, it's called, they are coplanar. Okay, if they are coplanar, meaning that they lie on the same plane, so that number is 0 definitely. But let us see if they are not coplanar, and then what will happen to that number. So how can I interpret that number from geometrical point of view? Yes? So drawing the picture would be a little bit hard, so I think it would be better if I use GeoGebra somehow, but let me try first. So assume that this is vector u. Okay, so I will draw it in this way. Assume that this is vector v. So it's going more or less behind the whiteboard somehow, yes? And then let us assume that this is your vector w here. I don't know if I could give, I will demonstrate it using GeoGebra, but try to see it as a solid object in a space, yes? So, and then, this is the case. Even if they are not from the same point, I can parallel transport them to the same point, so that's not a big problem, yes? And then, I want to complete this solid object. It's called parallelepiped. Yeah, parallelepiped. It's the three-dimensional version of a parallelogram. Yes. So it seems that you have a parallelogram on the floor, and then you take a copy of that and move it upward. You translate it upward. Yes. So that would be a parallelepiped. Yes. Okay. So if I can draw that, let me see. So this means that this would be more or less a parallelogram. Yes, and then, no, how should I draw that? But I have to parallel transport them here, yes. Is that right? No. So this should be parallel to this one from here. It's not parallel. Yeah, drawing it a little bit hard. So this one is at the back. So let me do this like that, it's easier. It's a little bit crazy, I cannot see it from this. So what will happen? Do you see? So this should be parallel to this one, but I don't know, let me just follow the logic, yes, instead of intuition. And then can you see how should I do that? Yeah, the point is that I am making a mistake. This is the mistake line. So this should be parallel to that V. This is why it's making a problem for me. Yeah, something like that. Yeah. So this should be parallel to this one. This should be parallel to this one. This should be parallel. So each one of them is actually a parallelogram. This object, this solid object, I will make it a better picture for you here, is called a parallelepiped, yes? And then we want to see that this is the volume of that. So this number that you get from here, of course this number might be negative, because the dot product, if the angle between this vector and that vector is an obtuse angle, it becomes negative. But if you take the absolute value, you get a positive number. That positive number is actually the volume of this. So by the way, so if I ask you what is a parallelepiped, parallelepiped is actually the three-dimensional version of a parallelogram. In a parallelogram, I have four sides. They are parallel. The ones that are opposite to each other are parallel. Yes? That is also the same thing for a parallelepiped. But I have six surfaces here. The ones that are opposite to each other are parallel planes. Yes, that is the three-dimensional version of parallelogram. Okay, for example, do you remember if I ask you, is a square a parallelogram? What is the answer? Is any given square a parallelogram? The answer is yes, because even in a square, the opposite sides are parallel. We have more properties, of course. Is a rectangle a parallelogram? The answer is again yes. But is a trapezoid a parallelogram? The answer is in general no. Yes? That is the same thing. Is a cube also a parallelepiped? The answer is yes. Is a rectangular cube also a parallelepiped? The answer is again yes. But this is the most general one if you want to talk about it. Okay. So how should we prove this? I want to remind you about something. First of all, it's a geometry problem. By the way, I think you should be able to tell me what is the volume from geometry point of view. So assume that you have precise measuring tools and you really want to measure the volume of this object. What is the volume of that object? Do you know it? It's exactly the rule for the volume of a rectangle or a rectangular cube or cube itself. So that is the area of the surface multiplied by the height. So the volume of this, the volume, if I show it with V, the volume is the surface area, the area of this bottom surface, and then multiplied by the height, h. By the way, we don't have any problems with S. Yesterday we learned that. So what is S? S is the area of this parallelogram, and these two vectors are adjacent sides of it, yes? So for this one, I don't have any problems. It becomes norm of U cross V, agree? Multiplied by H. The problem is that I do not have H yet. I have only U, V, and W. So far this is good because it is written in terms of U and V and I have them, but H is not good. I want to get rid of H in favor of U, V, and W. Yes? And I hope that you agree with me somehow in this H, this W should be involved. Because if this W is longer, the height is also longer, yes? So it's somehow, H should be somehow related to the length of this W vector. But let me change my color and here remind you of something. If you can go back to your notebooks, to your notes, so you will see that. Do you remember we talked about orthogonal projection? If I have a vector A, so let me call this, if I remember, I called this vector B when I was teaching you, and this vector, let me call it vector A, or I don't know if I call it U and B, but let me call them A and B. Do you remember, if I draw a perpendicular line from the tip of this vector to this vector that you see here is called the projection, do you remember? The projection of vector A onto vector B. Yes? If you just go a few pages back, you will see something like this, and then we got a formula by the proof. Of course, I proved this to you. We learned that projection of vector A onto vector B is equal to A dot B divided by norm of B squared multiplied by B. So that is the projection vector. Agree? If you have forgotten, you can go back. Unfortunately, that was exactly the video with a low quality of voice, so I just put it on the Google Classroom without putting it on the YouTube channel. But this was the formula we got for the projection vector, this vector. And if I ask you, what is the length? Let us calculate the length of this vector. So the length of projection vector A onto B is equal to the length of that combination, yes? So it becomes the length of A dot B over norm of B squared multiplied by B. But how should I interpret this? A dot B is a number, norm of B squared is a number, so this is totally a number. Number multiplied by a vector is a vector, and I'm asking what is the magnitude of that vector. But what can I do? Do you remember? Norm of any number multiplied by any vector is equal to the absolute value of your number multiplied by the norm of your vector. This we also have, yes? So what can I do? I can write the absolute value of my number multiplied by the norm of my vector. But this is absolute value of a fraction. This can be written as absolute value of the numerator divided by the absolute value of the numerator multiplied by norm of B. Here I cannot just suppress this absolute value sign because A dot B might be negative, might be positive, or even 0. So I really need to keep this absolute value sign because I'm not certain about the sign. But here I really don't need it, yes? Because whatever B is, norm of B squared is a positive number, so I really don't need this absolute value sign. So I can just take it away. And this number and that number can be simplified, yes? So this becomes absolute value of A dot B divided by what? Norm of Is that understandable? So we calculated the length of the projection vector in terms of the vectors themselves, yes, A and B. So now here, let us try to understand that. So if I cross product U by V, what will happen? This is good. Why? Because I want to find the height. The height will be perpendicular to this place, to this plane, yes? So if I want to make a vector perpendicular to this plane, which contains these two vectors, the thing that comes to mind, if you know vector calculus, is to cross product them, because automatically V cross W becomes a vector which is of course perpendicular to that plane, yes? Of course, I don't know the length. In this way, U cross V should be upward, but I don't know exact value of this length. It depends to the magnitudes of this and the angle. But whatever it is, it lies on this direction. So let us pretend that this is U cross V, okay? The only uncertainty about this is its length, because I don't know the length here exactly, and I don't know the angle. But that would be like that, yes? Okay. I don't know, if I draw this picture using GeoGebra, hopefully you realize. Do you agree with me? I don't know, can you imagine? If I project this W onto this red vector and calculate the length of the projection vector, it becomes exactly the height. Is that understandable, everyone? So it means that I project it here. If I ask you what is this vector, you would say this vector is... Let me change my color. So this vector is the projection of W onto which vector? Onto U cross V. Yes? This is that vector. But I hope that you agree with me, this H that I am interested in is equal to the norm of this vector. If I can calculate the magnitude of this vector, it becomes exactly the height. Yes? Understand? Okay, but let me calculate this. We have the formula. So let us just use that. This W here is playing the role of A. It is the vector which is supposed to be projected on. And then this U cross V is playing the role of this vector B that I want to project onto it. And then look at the final formula. I have an absolute value here. I have to multiply dot product A and B. A is this one, B is this one. Oops, I should have guessed that this will be in the wrong order. But anyway. And then what will happen? This divided by the norm of B. What is norm of B? Norm of this one. Yes? Okay, so this is my H, and then put it back into this formula. So V is equal to U cross V norm multiplied by H. H is that guy. But whatever this is, that is the same number. So they are cancelled. And what you get is the absolute value of this triple product, but unfortunately in this order. Now I realize when I was writing this book, I changed the letters in a different way. I was thinking why I did this. Now I understand why I did this. Because this is not exactly what I defined for you. But that's also triple product, yes? The triple product between U, V, and W. So at least you understand that. So if I ask you what is the interpretation of this triple product, you would say that if I make a parallelepiped so that these three vectors are adjacent sides, are the sides emitting from the first point, from the same point, then this number absolute value is the volume of that parallelepiped. Yes? Is that clear? Okay, one more thing is, what do you think? So here you see u and v are the vectors for the base surface. Yes? What do you think will be for the one that I started with? Do you think this will be completely different number? So you remember I defined you in that way, but I got this for this volume in this picture. Do you think this would be, what is this one? If this is the volume, what is this one in this picture? Yes? It's the why? Can you have a feeling why?
It's just the base.
Yes, instead of putting this object on the ground on this base, I can put it in the other base, yes? So that would be exactly the same thing. So if I choose this one with that one, if I rotate it and put it back on the ground so that that surface would be the surface on the ground, I would have get the same formula here. So, and that's a very nice property, by the way. So it means that if now go back, this means that W, this number and that number are the same. When absolute values are the same, it means that what? The numbers are either the same or opposite inside, yes? Because absolute values are the same. The absolute value here represents the volume of this object. This is also the volume of that object. So this absolute value and that absolute value should be the same. So it means that the expressions, the numbers inside the absolute values are either equal or negative of each other. Yes? But this, of course, I don't know, can you see that which one is in this case? In this case, is it positive or negative? Yes?
Should be positive
What?
volume is positive.
Pardon?
Volume is positive.
No, volume is positive, and this I have to put an absolute value because there is no guarantee that this number turns out to be a positive number. By the way, I didn't put absolute value by hand. You see that I was using this idea, absolute value comes into the game, and then this absolute value you see here is exactly the same absolute value that I put here. So I didn't put something by hand there. By the correct calculation, I got this absolute value. And this is sensible that I really need absolute value, because a dot product in general could be a negative number, which becomes meaningless. But when I put absolute value, I am on the safe side. But now I am saying that if this volume, this number with absolute value is the volume, this number with absolute value is also the volume. So this means that absolute value here and absolute value here are equal. So it means that either the numbers inside are exactly equal or they can differ by at most a negative sign. Yes? But I want to say in this case, in the way that I have written these vectors, is it positive or negative? I don't know if we can imagine it or not. Can we imagine that? I don't know what I have written here. Probably I have just written it. But now I want to think, can you say that in this picture, is it positive or negative? Because u cross v is exactly this vector in this direction, and this w, and make it, in this picture at least, this is an obtuse angle. Yes? In this picture that I have. So this means that this is itself a positive number. But even in this picture, can you imagine this one? It would be a little bit harder to imagine, yes? Because what would be V cross U in this case? V cross W? In which direction would be V cross W? Yeah, V cross W becomes a vector coming out from the board in this direction, yes? Perpendicular to the plane at the end. And that angle with this one is again an obtuse angle, an acute angle. I made a mistake. The previous one was also an acute angle, yes? So it means that this is also positive. So I need to take it away. Okay? And this is complete. This is called cyclic property or cyclic property of the triple product. So it means that if the way that you read it doesn't change, they are the same. Otherwise, they differ by a minus sign. So you see, I start from U, and then go to V, and then go to W, and then go to U. Here, I have started from U, U, V, W. Here, I have started from W, but I have gone in the same direction, you know, clockwise. I am going clockwise all the time. W, U, V. Can you tell me another way of writing it now? So here I started with U, but I'm always going clockwise direction. Here I started with W, now here I want to start with V. What can I write? V dot what?
W.
W cross U. So if you pay attention to this, all of them are equal. Yes? But of course, if I change this, then I will pick up a minus sign. Yes? So that is an extremely important property. That's an extremely important property of a triple product. I don't know which pronunciation is correct, cyclic or cyclic?
Cyclic.
Cyclic property of a triple product. It is extremely important. Of course, it doesn't mean that if I interchange them, you don't know the answer. If I interchange them, the answer picks up a minus sign because U cross V and V cross U differ by a minus sign. So it is very, very nice property, you see. So I misspelled that. It is parallelepiped. So please fix that one. Yes, that is not an. It's not an O. So and then let me check. Yeah, I think.
Parallelepiped.
Yeah, that is the pronunciation.
Parallelepiped.
And this is the spelling, so that was wrong. Yeah, fix it please. And then let me also check. I think triple is correct, or triple is correct.
Triple.
Triple is correct, yes?
Triple.
Yes. And let us check also that cyclic, or cyclic, I don't know. I have heard both of them, but I think...
Cyclic.
Yeah, it's cyclic. American pronunciation is at least cyclic, yes? Because I remember
Cyclical.
cyclical, but cyclic. So,
Cyclic.
yeah, it is cyclic. So, yeah, I don't know, it doesn't matter. We're learning mathematics, but it's also good to learn the correct pronunciation. Okay, well, of course, this is an American pronunciation. Might be English pronunciation is different. For example, I think American pronunciation, they say dimension. British say dimension or something like that. Or something probably. Okay, so that is extremely important. Now we have a good interpretation for the triple product. Okay, but there is something interesting. We learned that, now you understand that why if U, V, and W are all coplanar, then this number should be 0, from another perspective. Why is that? Because what will happen to this poor parallelepiped then? It is called a degenerate parallelepiped. And then you sit down on that, and then it's smashed on the ground, and then it means that the volume becomes 0. And then when the volume is 0, that number should be 0. That's also another way. But the point is that the other way around is also true, and that is important too. It's not trivial. If someone tells you that, how can you find, I give you 3 vectors, and I ask you, are these 3 vectors coplanar or not? This is extremely important. Now you know the answer. How should I understand? What is the criterion for understanding 3 given vectors are coplanar or not? Yes?
That when you use the triple product, it should become 0.
Yeah, so that is extremely important to realize now. So let me write this as a very important remark. Three non-zero vectors, U, V, and W are coplanar if and only if, IFF means if and only if, U dot V cross W is the 0 number. So remember this trick. This is one of the best ways to show that 3 given vectors are coplanar. Yes, you construct any kind of triple product. It doesn't matter in which order you put them at all. If this turns out to be 0, you are done. But before finalizing this session and then try to demonstrate it using GeoGebra a little bit to have a better picture, that's a really poor, now I understand what's going on. My brain was blocked at that time, so I should also draw this slide, yes. Okay, so here, we want to also find the volume of the pyramid made on this one. Again, pyramid is correct or pyramid? Let me check that one as well, yes.
You didn't say pyramid, då är jag helt distraught.
Det
känner jag gjort helt fel.
Pyramid.
Pyramid, yes. Okay, so pyramid, we want to measure the volume of the pyramid. So you know, then because, yeah, pyramid here, of course not all the pyramids here, only the pyramid here that I have its base, I want to have its base a triangle. It's called a tetrahedron. Yes, it has 4 sides. Because pyramid, in principle, you can have a pentagon on the ground, okay, and then you can have a point outside and connect this point to the vertices of a pentagon. That's also called a pyramid. Yes, and the pyramid in Egypt is the base is a square. That's also called a pyramid. But this one is a pyramid whose base is actually a triangle. That is called a tetrahedron because it has 4 faces, 3 faces and 1 in the bottom. Yes, that is called a tetrahedron. I want to measure the volume, calculate, not measure. I want to calculate the volume of this tetrahedron so that these 3 vectors are actually coming out from one vertex. You don't need to do heavy calculations. Do you remember the formula for the volume of any pyramid? It is very similar to SH, but you have a factor behind that. What is that?
1/3.
1/3. So that factor is 1/3. So if I want to calculate this, you usually have it in the formula sheet. Probably you'd ever use it because you didn't have those questions, but that is always in the formula sheet. How can I find that? That's a different story. We go back to that later in Math 4. Okay, but here, let me just use it. So the volume of the tetrahedron not tetrahedron, any pyramid, but here we only want to talk about this tetrahedron, is equal to 1/3 the area of the base multiplied by the height again. Okay, I hope that you agree with me here. I don't need to calculate height again, because the height of this pyramid is exactly equal to the height of this parallelepiped, yes? So that h that I calculated from there is still working. So what the only difference is that is the area of the base is changed. But that's also not a big deal. That's just half of the area of the original base. So what I have to do, so if you don't mind, yes, let me write this little s. Okay, so instead of capital S, let us reserve capital S for this one. So let me write little s here. But if I ask you what is little s, you would say little s is 1/2 of the capital S. Yes, and this is h. And then 1/2, 1/3 becomes 1/6 capital S h. So be careful. If you want to write it, the factor is 1/6 here. And I already calculated capital S. Yes, that is norm of u. I already calculated this part, by the way. What was that part? It was 1/6 absolute value of w dot u cross v. Yes? So don't get confused. If you use the formula sheet, the factor for the volume of a tetrahedron is 1/3. But if you want to use vector calculus, and this would be 1/6 of that triple product. Yes? So this is also something I want you to know. So I don't know, let me see if we can do some GeoGebra here, but let me this time, I want to test another idea, so let us see how this will work. Just start recording, but I want to switch to another camera, Alt 2, yes, okay, okay, so you can see that here. Let me try to see, let us try these ideas together. So I would prefer to go to View here, and then I go to 3D graphics. Yes. Let me see. Okay. So what is? Let me keep also this 2D. So you know that I'm alternating between these 2D. So if you want to draw a parallelepiped, I don't know. We can go here. We can open the grids, and then if you don't mind, let me just start rotating this, so that I can have from above this plane, and let me make some parallelogram here for you. Here, oops, it's very thick, but anyway. Oops, I think this is a parallelogram, agree? So that is a parallelogram, but let me go back to space now. Sit my space tube. Yes, now we are in space. So here, that is the same parallelogram. But I don't know how to draw it, because I checked GeoGebra, can draw pyramids and can draw prism, but it cannot draw this parallelepiped as some instruction here. So I don't know, the way that I was thinking when I was in the train is we can, that's also good to learn from vectors. So what I want to do, I want to translate this parallelogram into space. Yes, in some way. But I want to do it uniformly. So one way to do that is to make a vector. So what can I do? Let me by the way put a point here. Which points has been used? Let me introduce a point. I don't know, I just 1, 2 and 3. 1, 2 and 3. Yes, and then this is my point. Then I will make a vector here. I go here to instruction vector, and then I make that vector for you from here to here. Oh, it's very thick now. Anyway, and then I want to translate every point in the parallelogram by that vector into space. And there is this, I remember that there is something here. So what you do, you go to this three-dimensional, but you choose this vector from a point. No, sorry. Here, you go to translate by a vector. You choose this one, and then I click this point, and this vector, it's already translated into space, yes? But along that, it is a little bit, it seems that this is longer, but it is not. This distance from the origin to that is exactly the same length as here, if you see it. I can rotate it, and probably you can see it here, but let me, you see, they are of the same height, but if you see, that's exactly the translation of point D into space along this vector that I have just randomly defined a vector for you. This vector, this thick vector, is just a random vector that I made, and I want to translate all these parallelogram using that vector. So it means that what I have to do, again, I take this one, yes, and I point here and there. I get another one here, and oops, what is happening, I don't know. So another time, this point and this vector. Now it is in space, yes? And now I make another polygon using this. Yes, it's working. So now you see I translated the lower parallelogram into space using that vector. Now this vector, I really don't need it anymore, so let us get rid of it as soon as possible. Yes, and now what I do, I make this polygon rule again, then I will start making it complete. Yes, I don't know, this is probably, I'm not saying this is the optimal way of making a parallelepiped, but at least it works. Okay, I have to complete this one as well. Yeah, I think it's good, yes. Oops, where did I start from? Do you remember? Here, yes. So this is something is a parallelepiped, yes? Now I hope that you can have a feeling about that. So let me make it a little bit bigger for you. We don't need this one. And by the way, we probably don't need the axis. So this is a parallelepiped, yes? Is that understandable? Okay, so at least you have a feeling about that. But now, let us check some of these ideas we had using GeoGebra. So if I want to compare this picture here with the one that I drew, so let me make another vector here. Vector, for example, from point A to point B. Yes? And then vector from point A to this point behind that. It's not clear, so let me make it somehow clear. Let me rotate it a little bit. Okay, so now I can do that. Yes? So these are two vectors, and then let me do another vector from this point to that point. So is that clear what we are doing? We have these three vectors, and now if I cross product them, what will happen? So I don't know what are the names, so hopefully this I would write here cross vector and vector. So which vectors are these? Do you see them? It is V and W, thank you. So V, and I go here W. That is my the cross product. So this is vector U, this dotted one is vector V. If you cross product these things, this becomes this vector. And you see that that length is not under my control. The length of this cross product depends on the lengths of these two vectors and the angle between them. So if I start changing them, it will change. But the point is that I know the numbers, I remember. So let me define another point for you here. So I don't know actually how should I do that. So how should I go below this? Anyway, so okay, that's good. So now I will give you another point. Let me call it, I don't know, a letter that is not being used so far. I will give it, for example, x and y should be 0 and 0 and 3. Yes, and that is z. And then I will have this vector again from this one to that one. And let me change the color here. So let me make it red, for example. And it doesn't show. Okay, so let me make this black. Make the previous one red. Yes. No. This one. So I have to choose this one first, I think. I don't know why it doesn't work. Okay, it works, hopefully. Anyway, I don't know why this. I really don't like these features in GeoGebra. But anyway, so this vector that you see here is exactly the orthogonal projection of this vector onto that cross vector. How can we see that? Because if you want to see this, I just need to take this point E and connect it to the tip of this arrow, and then I can go here and measure this angle. Yes, and you see that's 90. Yes, so what we did is actually we were able to calculate the length of this red vector, which is h. I hope that you can see that this length, which is the orthogonal projection of this vector onto the cross product, is exactly equal to the height. If this is not very clear from this perspective, I can hopefully convince you that yes, you see that the length of that red vector is exactly equal to the height of that object. So that is exactly what we did when we were calculating this. Okay, is that understandable? And then I think we had a pyramid here, so let me see. Extrude to a pyramid. So what I can do, I can also do this triangle. Then I will go here and extrude this to a pyramid. If I am right, I use this option. I click on it, and then what is the altitude? I would say 3, and then I don't know. So that is the tetrahedron. We measured its volume there. So let me now choose that one. So you see, that was the volume of the tetrahedron. No, that is not the tetrahedron. No, it's.
I think you had another option.
You clicked. No, you clicked.
No, it's actually a pyramid, isn't it?
Yeah, it's a pyramid.
It's a pyramid, but yeah.
It's
So the vertex is, the head is here actually. Yes, so that's a pyramid. Yeah. But anyway, that's also good to work with GeoGebra to learn these things. Okay. So hopefully I could convince you that what we did, even though my picture was poor, but that is a better picture. Yes? Any questions? Okay, so let me now, I have to switch to the first camera. And then I have to turn this off. Okay, so I can complete it in one more session, but mainly we are done. Nothing serious is left from this, except one very important theorem that we will not be able to prove it right now. We will be able to prove it later, and I will prove it for you later, definitely. But let me give you some examples, at least one example together, and solve it together. Example. Okay, this is a good example. Simple but efficient. You know, it gives you the importance actually of this remark. So, U, V, and W are non-zero vectors such that we have this property. U cross V plus V cross W plus W cross U is the zero vector. It's not always guaranteed that this combination is the zero vector, but they are oriented in a way, in a space, so that when we add these three vectors, it turns out to be the zero vector. Show that U, V, and W are coplanar. Okay. Let us do it together. I don't know, might be you can have a good reasoning from geometrical perspective. I'm not against that. But let us use algebra if possible in that case. That is good. If you are curious, you can try to think, is it possible using geometrical argument regarding the orientation of these vectors in space? Can you cook up an argument so that if this is the case, these three vectors have to be coplanar? Of course, one way to think is that if they are not coplanar, what will happen? Yeah, something like that. But let us use algebra here. And this important remark. This is an example to give you how to use this remark. So I want to show that these three vectors are coplanar. According to that remark, if I succeed to show that this triple product is equal to 0, I am done. So the strategy is clear. My goal is to calculate that triple product using this assumption. Now I want to hear from you. Do you have any opinion about what to do? If you know algebra, I don't know, your algebraic skills are good, you really probably immediately find what to do at least. It might not work, but at least it is very clear what to do. This is my assumption. I want to say something about that combination. It's as simple as that. So what should I do? Yes?
Maybe you switch W and U, and then you factorize out U.
No, be careful. What is the point of that? I told you the point, I want to have this combination. How many vectors are involved here? 3. But in each term, how many vectors are involved? 2. So it means that manipulating this exactly like this, it will not work because it will not give me an extra vector in any term. That is why exactly what I want you to learn. When you reach to this level, you have to be very quick in deciding these things. Might be these are not working, but at least they are natural. So I want to go from here to a combination of 3 vectors in that form. What is the first natural step you have to take? Just dare to guess. Okay, what is the supernatural way to do that? Because probably you don't have anything with natural things, yes? So is there any supernatural way to do that? Yes?
Do the dot product
With
one of the vectors.
one of the vectors. So you see, you want to have u dot, it is crying out how to do it. U dot v cross w. So just multiply it by u, see what happens, yes? Because if I dot product u, what will happen? This middle term becomes exactly what I want. Of course I will get some extra terms, we will think something for it later. But at least it's a natural step, yes? So what I do, you are telling me that this combination is 0, then if you tell me this is true, then you have to admit that this is also true. I want you to follow my logic. Is that logic understandable for everyone? If you tell me that this is the 0 vector, you have to admit that this is also true. Because I just dot product both sides by u. Is that understandable, yes or no? On the right hand side, do I have any problems? What is the answer?
0.
0.
Oh, 0. It's 0.
Just 0, not vector. Yes, that's dot product. And then, can I use distributivity here? It's natural, isn't it? So it becomes u dot u cross v plus u dot v cross w, which is my goal, plus u dot w cross u. Okay? Then what? At least I have something that I like it. I need to get rid of these two. But it is just a matter of seconds if you have done your homework. Or if you can imagine it immediately. What is this combination?
Oh, when you dot product the cross product with the same one inside, it becomes
zero. Yes, because u cross v by definition is perpendicular to both u and v, and then you are multiplying by u. So this number is 0. For the same reason, this number is 0. 0 plus this one plus 0 is 0. So it means u dot v cross w is 0. And then they are coplanar. Or coplanar, yes? Yes, is that understandable? I just write one exercise here, but we will not solve it. I want you to solve it. So I will use one more session to complete this chapter, this section, and then we go to analytical way, which is very important. Analytical way of treating the same topic. Everything we learn, we want to do it numerically. Yes? Everything. Vectors, addition of vectors, subtraction, multiplication, dot product, cross product, everything. Okay, so let me write an exercise. U, V, and W are non-zero vectors that don't lie on the same plane. Yes? Show that vectors V plus W, comma, the other one is V minus 2W, and 2 times U plus V plus 3W are not coplanar. So let me, they are, so the first 3 vectors that I start with are not coplanar. We make a combination, these combination, U and W, V and W are added, this combination and that combination. We want to guarantee that it is not possible for this combination to be coplanar. Yes, that's a very easy exercise. This uses exactly this remark. I want you to think about these. So you see that thinking about this problem from geometrical point of view is not that easy to visualize all the things, because I need to consider all the ways that we have U, V, and W, and then construct these vectors in my head in the space and see that they are not coplanar. But algebraically, it is easier to do this problem. Yes? Okay, so we end here. Thank you.